So we're going to be doing the following problem. We're going to show that the vector field given by f of xy is equal to x over the square root of x squared plus y squared, comma y over the square root of x squared plus y squared is not conservative. And we're going to be doing this by showing that the line integral of f is not path independent. We're going to draw a picture here. So we've got our x-axis and our y-axis. And we're going to create two different paths with the same beginning and end point. So we're going to start at negative 1 comma 0 and we're going to go to 1 comma 0. So let's draw that out. And the two paths, one is going to be along this circle connecting the 2 points, and the other is just going to be the straight line connecting them. And we're going to compute both of these line integrals. So the red line is going to be a bit easier, so we'll do that first. We're going to call this curve C1. And we'll parameterize it as r sub 1 of t is equal to t comma 0, where t ranges between negative 1 and 1. Now, the derivative of this, so r sub 1 partial t, or prime t, is equal to 1 comma 0, and now it's time to set up our integral. So the integral from negative 1 to 1, so we're going to plug in our parameterization into our function capital F. We just end up with 1 comma 0, and then we're dotting that with r1 prime of t, which is 1 comma 0 dt. So this comes out to be the integral from negative 1 to 1 of 1 dt, which is the length of the curve, which is just 2. Alright, so we'll circle that and move on to our other curve, which we're going to call C2. Now C2 is a little trickier, but not much more. So R2 of t is equal to, I'm going to use the parameterization negative cosine of t, comma sine of t, where t ranges between 0 and 2 pi. 0 and pi. Now the derivative, r sub 2 prime of t, is equal to sine of t, comma cosine of t. And now we can set up the integral. So we have the integral from 0 to pi. Again, I plug in my parameterization for r2 of t into capital F, and because the square root of x squared plus y squared is just 1 in this case, I just get r2 of t. And I dot that with the derivative. So expanding this out, I get the integral from 0 to pi of negative cosine of t times sine of t plus sine of t times cosine of t. Well, these are equal, so they're going to cancel out, and I'm just left with the integral from 0 to pi of 0 dt, which is clearly 0. Now I'm going to erase a little bit and then write out my conclusion. So, what we've seen here is that since 2 is not equal to 0, then the line integral of f cannot be independent of path. Therefore, this tells us that f cannot be conservative, since conservative vector fields are independent of path. So, something to check on your own. Normally we show this by showing that partial p partial y doesn't equal partial q partial x. Take a few minutes and try this out, and you'll see that in this case they actually are equal. The reason why it doesn't work in this case is because you'll notice that this vector field is not defined at 0, 0. So the region it's actually defined over isn't simply connected, which means that showing partial p partial y equals partial q partial x is not enough to show that the vector field is conservative.